So this term we can actually approximate with the Simpsons rule. So for the Simpson rule, we have had integral from a lower and the upper boundary of a function which is dependent on x times dx. We can approximate it as delta x divided 3 times f as a function of the lower boundary plus 4 times f as a mean value between the upper and lower boundary, namely xu plus xl divided 2, plus the function of our upper boundary. And in our case, the fx would be 1 divided negative r as a function of the conversion. And in our case, the upper boundary xu is going to be equal to the conversion a2, and the lower boundary is going to be equal to the conversion a1, and this delta x is going to be equal to the upper minus the lower boundary divided n. So n is the number of our subintervals, and here we have the conversion a1 and a2. Hence we will have two subintervals, so n is the numbers of subintervals. Here we have conversion a1 and conversion a2, meaning that n is equal to 2. So delta x is going to be equal to the conversion a2 minus the conversion a1 divided n. So applying the Simpson rule in our case, we can say that the integral from the lower boundary conversion a1 to the conversion a2 of our function, which is 1 divided negative the reaction rate as a function of the conversion, times the conversion species A at position C, can be estimated as delta x divided 3 times negative 1 divided Ra as a function of the conversion a1 plus 4 times 1 divided Ra as a function of the upper limit conversion a2 plus conversion a1 divided 2, this is negative, plus 1 divided Ra as a function of the conversion a2, this is also negative. So we will determine each of these value individually. And this is 4. So let's start with term number 1. So we know that delta x, we'll insert it just right here. So delta x is equal to the conversion a2, which we have given by our test, which is 0.7, minus the conversion a1, which is 0.3, divided n, which is 2, which is equal to 0.2. So here we have determined delta x. So for the second term, 1 divided negative RA as a function of conversion A1. This is 1 divided negative RA1, which we have given by the task, which is 1 divided 0.0086 mole per liter second. And this is around 116 liter second per mole. So we have determined the second term. And I will continue with the fourth term because it's quite similar to the second term. So 1 divided negative RA as a function of the conversion A2 is actually 1 divided RA2, which again we have given by the task. So 1 divided 0.0035 mole per liter second. And this is around 285 liter second per mole. So we will take a closer look at the term without the 4. So 1 divided negative RA as a function of the upper conversion plus the lower conversion divided 2. And this is equal to 1 divided negative RA as a function of 0.7 plus 0.3 divided 2, which is equal to 1 divided negative RA as a function of 0.5. Unfortunately, the reaction rate of species A at 0.5 is not available, so we need to use further approximation methods, and we will be using linear interpolation. So to understand linear interpolation, let us discuss this plot. So on our y-axis we have 1 divided RA as a function of the conversion. The unit is liter second per mole. And on the x-axis we have the conversion of the species A, which is dimensionless. By the way, the y-axis is negative. So if we have the value of 1 divided RA as a function of the conversion A1, which we just have determined, and this is 116 liter second per mole. So let's plot this dot in the graph. So here the x point would be conversion A1, and we have also determined negative 1 divided RA as a function of the conversion A2, which was 285 liter seconds per mole. And for this point the x-axis would correspond to the conversion A2, and this was 0.7, conversion A1 was 0.3, and what we want to find out is our reaction rate at the conversion 0.5. So here we would have negative 1 divided RA as a function of 0.5. And what we are going to assume is that within this range we have a linear relationship, meaning this correlation can be graphed as following within these boundaries. So linear interpolation is being used as following. So negative 1 divided RA as a function of 0.5 is going to be equal to negative 1 divided RA as a function of conversion A1 plus 0.5 minus the conversion A1 divided the conversion A2 minus the conversion A1 times negative 1 divided RA as a function of the conversion A2 minus 1 divided RA as a function of conversion A1. And if we insert the values, negative 1 divided RA as a function of 0.5 will result in 116 liters second per mole plus 0.5 minus 0.3 divided 0.7 minus 0.3 times, in parentheses, 285 liters second per mole minus 116 liters second per mole, which will lead to negative 1 divided RA as a function of 0.5 being around 200 liters second per mole. So this is our fourth term. So we have now determined all of our values. So we can now insert them in our equation. So our integral from conversion A1 to conversion A2 of 1 divided negative RA as a function of the conversion times D, the conversion of the species A at position C, is going to be around 0.2 divided 3 times 116 liters second per mole plus 4 times 200 liters second per mole plus 285 liters second per mole, which will result in around 80 liters second per mole. So, as we previously discussed, the volume of the PFR is going to be equal to the molar flow rate FA0 times the integral from conversion A1 to conversion A2 of negative 1 divided RA times D conversion A position C, which we just have determined is equal to 30 mole per second times 80 liters second per mole, which is equal to 2,400 liters. And now we take a closer look into our last reactor, and we will use the same procedure as CSTR1. So let's quickly go through it. So we will do a species balance for the species A for the CSTR2. So the change of the species A with respect to time is going to be equal to the entering molar flow rate, which is FA2, minus the leaving molar flow rate, which is FA3, plus the reaction rate of the species A, RA3, times VCSTR2. Again, for the Fi terms, we will use Fa0 times 1 minus the corresponding conversion of the species I. So this is 0 because we have steady state, so 0 is equal to the entering molar flow rate times 1 minus the conversion A2, and Fa3 will result in, well, minus Fa3, which is Fa0 times 1 minus the conversion A3 plus RA3 times VCSTR2. So in the previous task I have rearranged the equation to solve for VCSTR, so we will use the same procedure as VCSTR1, resulting in VCSTR2 being equal to Fa0, in parentheses, the conversion A3 minus conversion A2 divided negative Ra3, and if we insert the values from the test, so this is 30 mole per second FA0, so 30 mole per second times 0.9 minus 0.7 divided 0.0015 mole per liter second is going to be equal to 4,000 liters. So in summary, the VCSTR1 is equal to 1050 liters, the VPFR is equal to 2400 liters, and VCSTR2 is equal to 4000 liters.